Hello, my name is Hantran. In this video, we're going to be using Python to perform a flash calculation using the Rachford-Rice method. So in this video, we're going to be just coding out the Python code. In a previous video, we actually derived the equation and we went over what a flash calculation and a flash drum is. So we're going to do a quick review before we head straight into the code. And so this is what was done in the previous video. And so here we have a flash drum, and going into the flash drum is a feed, and coming out of the flash drum is vapor and liquid, and each of those having a vapor mole fraction. So the vapor has a vapor mole fraction and the liquid has a liquid mole fraction. Additionally, the feed has a feed mole fraction as well. And so what we did was we established some mass balance equations, which is that the feed going in is going to equal the vapor plus the liquid that's coming out. We also talked about the ratio, and so the mole fraction ratio is the vapor mole fraction over the liquid mole fraction, and we used all of this information and just some algebraic moving around of terms to come to the conclusion that the summation of the fraction, where the numerator is the feed mole fraction times the quantity of the mole fraction ratio minus 1 over the 1 plus the vapor feed ratio, or vapor over feed, times the quantity of the mole fraction ratio minus 1 is equal to 0. And so what we have here is we have an equation with one unknown that we can solve to find the unknown. And so what we will be doing is we will be solving for the vapor feed ratio, so the vapor over the feed, and using that to solve for the vapor amount, the liquid amount, and the vapor mole fraction and the liquid mole fraction. And so we have a problem here where we are given a set temperature at 393 kelvins and a set pressure at 150 kilopascals. So we're also told that there are 4 moles of benzene per second and 6 moles of toluene per second. So that gives us a total of 10 moles in the feed. And so if we were to do 4 divided by 10, that gives us 0.4 mole fraction of benzene, and 6 divided by 10 is 0.6 mole fraction of toluene. And so that is our given, and we are told to calculate the composition and the flow rates of the outgoing vapor and liquid phases. So we're going to head on over to our Python. So in a previous video in this series, we used the Python to code different functions for bubble pressure, bubble temperature, dew pressure, and dew temperature, as well as use that information to code out some phase diagrams. And so here we have some phase diagrams. In the top left corner up here, we will have liquid. In the bottom right corner, we have vapor. So in this middle area between the two curves is actually a vapor-liquid equilibrium, which is what the feed is. And so before we actually start writing new lines of code, let's review some of the old lines of code so we know what things mean. So what's really important is what we imported up here. So we imported numpy as NP. So when we use numpy later on, we will use it as NP. And what numpy does is it allows us to perform more advanced mathematical functions, so such as the summation that we'll be using. Numpy allows us to do that. We also imported CHE. So CHE is from this CHE tools. It's a repository that allows us access to many different equations that can calculate different aspects and different properties of different components. And so we will be using it to calculate the saturated vapor pressure. We have from SciPy to optimize, we have the import root. So root is a solving function that allows us to solve equations that are vectors. And so when we have a function that gives us an equation, we can use the root solver with that function equation and an initial guess that will solve the equation for the unknown that's in the equation as long as the equation that we have is set equal to 0. And so we have that equation here. We have the summation equation here set equal to 0. So that's the equation we'll be using, and that's the equation that the root solver will be solving. And so we also imported subplots, but that is for the plots that we have already plotted. So we're not going to be using that for this flash calculation. So we will be doing a Rachford-Rice flash calculation. And so the first thing that we will need is an equation for the root solver to solve. So we need to define a function for this equation. So we will just call it RR for Rachford-Rice. And there is going to be a vector. So the way the root solver works and how this equation needs to be set up is there's going to be a vector. And so we need to unpack that vector. And so what we're going to be getting from that vector is the vapor feed ratio. So we'll call it VF. And that's going to be the first index of that vector. And so now what we want from this function here is the equation. So we're going to put the equation in one part at a time. So the first part is the numerator, and that's going to be the feed mole fraction times the quantity of the mole fraction ratio minus 1. So the feed mole fraction times the quantity of the ratio mole fraction minus 1. And so that is our numerator. And then we have our denominator, which is 1 plus the vapor feed ratio times the quantity of our mole fraction ratio minus 1. And so that is our denominator. And so we need the sum of this entire fraction. And so we're going to use that numpy np dot sum. And we are going to sum up that entire fraction. And with the root solver that we'll be using, we need this to be in a vector form, so an array. So we're going to put square brackets around it. And this will return it as an array. So now, if we shift enter, we have all of these defined, except there are parts in there that we don't have defined, such as the feed mole fraction and the mole fraction ratio. So let's go ahead and define those. So the first thing that we want to define is mole fraction ratio. So the feed mole fraction ratio, we have a mole fraction of benzene and toluene. So if we go back up here to our previous code, we used the CHE props. So what this is it's that repository that we imported, and it goes to the properties of the different components. So this is benzene here, and it can get the information for benzene. And so we already have it written out as benzene and toluene, so we're going to have to input the mole fractions in that order. So benzene first and then toluene. And so we're going to, again, create an array because we have two mole fractions. And the first one we have is benzene, and so we have 4 moles per second out of 10. So 4 divided by 10 is 0.4. That is benzene. And then toluene, we have 6 moles. 6 divided by the total 10 is 0.6. And so that is benzene and then toluene. And then, so that is our feed mole fraction established, except it's an array. And so what we have to do is we have to use numpy again, dot array, and that will put this information into an array form. Next we have the mole fraction ratio. If we go back to the equations that we derived up here for the mole fraction ratio, we have it as the liquid or the vapor mole fraction over the liquid mole fraction, And so if we use Raoult's law, which is what we have up here, it is the liquid mole fraction times the saturated vapor pressure. It's the liquid mole fraction times the saturated vapor pressure equals the vapor mole fraction times the total pressure. So if we use Raoult's law as well as this definition of the mole fraction ratio here, what we come up with is that the mole fraction ratio is also the saturated vapor pressure over the total pressure. And if we set those two next to one another, we can see that if we cross multiply, so we have the liquid mole fraction times the saturated vapor pressure, that gives us the left side of Raoult's law, and we have the liquid mole fraction, or the vapor mole fraction times the total pressure, that gives us the right side of Raoult's law. And so the ratio is also just the saturated vapor pressure over the total pressure, and we can find the saturated vapor pressure through Antoine's equation because we are given a temperature and we are also given the set pressure. So we have the mole fraction ratio, and so that's the saturated vapor pressure divided by the total pressure. Well, the saturated vapor pressure is calculated using Antoine's equation, which we have through the CHE tool pack that we imported. And so to do that, we use the P, and then we use PVAP, that's the vapor pressure at a certain temperature. And so now what we need is the temperature and the pressure. Well, those are set values that we are given. So we are given that the temperature is 393 Kelvin and the pressure is 150 kilopascals. So the temperature is 393 and the pressure is 150 kilopascals. And so now we have our terms defined. And so now what we need to do is we need to use the root solver. So it's going to need first an equation. So our equation is the function that we just defined, and it needs an initial guess in an array. So we can just have an initial guess of 0.5. And if we shift enter, that gives us our answer here in the x, and it's an array form. So we want just the x value. We don't need this extra information here. So we want just the x value, and we want just the first value, the first index, although there is only one, but we just want it in a scalar form. So that is now our vapor feed ratio. So we can define it. And so now what we can do is we can calculate the vapor, the liquid, and the compositions of those. So if we go back to our equations here, we can see that the vapor liquid ratio, in order to figure out what that vapor is, we would just multiply it by the feed. So we are also given the feed because we are told that 4 moles of benzene and 6 moles of toluene, that gives us a total of 10 moles. So our feed is going to be 10 moles. What's next is we want to calculate our liquid. And so in this, we have that the feed equals the vapor plus the liquid. So the liquid is just the feed minus the vapor. And now we want our mole fraction. So we have down here the liquid mole fraction, which is the feed mole fraction divided by 1 plus the vapor feed ratio times the quantity of the mole fraction ratio minus 1. So we're going to input that right into our code. So feed mole fraction divided by the quantity of 1 plus the quantity of the vapor feed ratio times the quantity of the mole fraction ratio minus 1. And then lastly, we have our vapor mole fraction, which is up here, and it is just the mole fraction ratio times the liquid mole fraction. So now that we have all that calculated, we're going to print it. So the vapor feed ratio the vapor, see exactly what it's asking for, the vapor flow rate the liquid flow rate. So for our print statements, we are doing print, and in parentheses, we are then doing F and then quotation, and then the title of what we are finding. And then we are doing the defined variable. And then closing out the quotations and the parentheses. So that is for all 5 print statements. And let's label with some units. So this is moles per second. And then this is going to print out benzene and toluene. So let's label the order in which they will print. So if we shift enter, we now have all of our answers. So we have the vapor feed ratio, the vapor flow rate, the liquid flow rate. So the vapor feed ratio is 2.49. The vapor flow rate is 24.86 moles per second. The liquid flow rate is negative 14.86 moles per second. The vapor mole fraction is 0.11 for benzene and 0.88 for toluene. The liquid mole fraction is 0.23 for benzene and 0.77 for toluene. And that is our answers.